I'm Stephanie Burton. I'm the president of the Royal Society of South Africa, and that's why I'm opening this lecture this evening. I have a few brief words of introduction, and then we will move on to our speaker and listen to a lecture. We try to make sure that we stick to our time with these Royal Society lectures, bearing in mind that everybody has a schedule that they try to that they want to adhere to. So the idea is that we have these lectures on an early evening slot. We take about an hour, and we hope that during that time we cover the ground and have some time for questions and answers. So let me just start by reiterating my welcome and saying to you just two things about the Royal Society. It is the oldest multidisciplinary organization in South Africa. It was established in 1908, and it is open to anyone who has an interest in science. There is a very effective website, and if anybody is interested, if you simply Google Royal Society of South Africa, you will find it, but of course you are welcome to ask me or any of the other members of council for the web address. I am joined this evening by Professor Bert Klumpman, who is the Vice President of the Royal Society, and also some of the other members of the council, who are instrumental, of course, in deciding on our agenda. Okay, so we also co-host these presentations with the South African National Science Academy, which is a younger organization established in 1996, but by a statute of Parliament and also funded by Parliament. Before I start on further discussions, I would like to say a special welcome to three new members of the Royal Society of South Africa: Professor Rod Walker, who is in the Faculty of Pharmacy at Rhodes University; Dr. Josh Devines, who has just recently been reinstated. He's a lecturer at the University of Wits; and Dr. Daniel Lemley, who is a postdoctoral research fellow at Nelson Mandela University. So welcome to those members. I also want to just say that we have these talks on a regular basis, and we have a couple coming up in March and April, which we will of course advertise, but in March we will have Professor Alan Morris from the Department of Human Biology at UCT. That's the 15th of March. And then on the 19th of April, we will have Dr. Michelle Lochner from the Department of Astrophysics at the University of the Western Cape. So please do take a look at the website. You'll see updates, and we will send reminders about those talks. Tonight, we have a colleague who, as he said a moment ago in the casual chat, joined the University of Pretoria while I was in office as Deputy Vice Chancellor there, Professor Janek Banasiak. He is a professor in the Department of Mathematics and Applied Mathematics at the University of Pretoria. He holds a DST NRF Saatchi Chair in Mathematical Models and Methods in Biosciences and Bioengineering. And this evening, he is going to talk about mathematical models, successes, fads, and fallacies. You will have seen on our website, if you've looked on the adverts for this talk, a little bit of background to Professor Banasiak. He is originally from Poland, and I think he said a moment ago he is actually in Poland at the moment. But he has traveled to many different institutions and has taken positions in a number of different institutions, including originally at the university before the University of Pretoria, at the University of what was then Natal, now University of KwaZulu-Natal. He's also a visiting professor at a number of other different institutions, and he has been the recipient of various awards. He's the editor or a member of an editorial board of several of the leading journals in his field. He has been and served as the Vice President of the South African Mathematical Society, and he is a fellow of the African Academy of Sciences. So with that very impressive and very short summary of his CV, I'm going to just ask that he delivers his speech. I'm sorry, I'm trying to just get back to the screen. I beg your pardon. There we go. Sorry, my screen was doing something strange. Right, so let me hand over to our speaker for this evening, Professor Banasiak. We're very much looking forward to listening to you. And let me just say, I know from my experience that I'm not being a mathematician, I am going to understand this, and we're very much looking forward to hearing your presentations. So please go ahead. Once we've finished, I will ask my colleague, the Vice President, Bert Klumperman, to handle the questions and answers. And if we get pushed for time, well, then I will take over. But over to you. So thank you very much.
Thank you very much, Professor Burton, for a very nice introduction. And I'm very honored to have been invited for this talk. And as my good friend Igor asked me, I will try to do it in a popular way. This is a talk about items, about things which I have been talking about on several occasions. So I apologize if there are overlaps of this talk with some talks you might have heard before. So let us start. Okay, let me go here. Okay, so screen mode. Okay. Can you see the screen? Everything is fine?
Yes, yes, we can. Yes,
okay,
it's fine.
Great. Thank you very much. Okay, so we'll be talking about mathematical models and its place in mathematical sciences. So let us start to define, to talk about what we mean by mathematical sciences. So for me, mathematical sciences is sort of like a wide discipline which aims to understand the world by performing symbolic reasoning and computations on abstract structures. And in some sense, we can subdivide mathematical sciences into three streams. One is simply to discover and understand the relations among these abstract structures. We can refer to this stream as pure mathematics. We can try to capture certain features of the world by such abstract structures through mathematical modeling, analyze them and use for computations, and then interpret them to make predictions about the world. And this is what is commonly understood under the name applied mathematics. And then we can use abstract arguments and structures to make inferences about the world from the available data, statistics, and very fashionable field of machine learning, artificial intelligence at this moment. Okay. So, what is mathematical model? What the mathematical models are useful? Why mathematical models are useful? Let us start with a simple example, and in this example, simply a mathematical model serves as a very cheap laboratory. So let us think about toxic or radioactive waste, which is often disposed of by placing it in a hermetically sealed drum and sinking this drum into deep water, deep ocean. The problem is that the drum can crack upon hitting the bottom. Now, if we want to dispose really dangerous waste, then we would like to make sure that this will not happen, so the drum will not crack. How can we do this? Well, of course, one way is simply to send divers into a deep sea and observe drums hitting the bottom. But we can imagine that if, for example, we want to dispose these drums into sort of like one kilometer depth, then such an exercise would be very expensive and not very practical. So here we combine mathematics with experiment in a normal surface laboratory. So we can easily find that a drum can crack hitting a surface at the speed of 4 meters per second. We can actually simulate, accelerate the drum to this particular speed and drop such a drum onto the floor. Now, the question is, can we determine what will be the speed of the drum when the drum is sinking into the water, into the ocean, for example? Again, observing the sinking drum is not practical, so we resort to mathematics. So we simply simulate the sinking of the drum on a computer using mathematical model. Because not all of you are mathematicians, actually probably most of you are not mathematicians, there is a formula coming from the Newton's third law, which gives us the velocity of the drum at given depth y, and essentially the velocity depends on the mass of the drum, earth acceleration, displacement force, and the so-called drag coefficient, which is related to the fact that actually there is some resistance of the medium when the drum is sinking. And in this way, we can, using mathematical techniques, we can solve this equation and we can graph the speed of the drum at a given depth. And we can see easily that the drum in this particular case, in this model, will reach the sort of like dangerous speed of 4 meters per second, already sinking to the depth of more or less 5 meters. So we can see that in this scenario, disposing of toxic waste in this way is not really feasible. And we can do this without really performing too many experiments. We don't have to send we don't have to send divers to observe what happens really at the bottom of the sea when the drum reaches the bottom. So this is actually an example of mathematical model as a cheap laboratory. Now, for applications of mathematics, a crucial question is how we connect our mind, our reasoning tools to the external world. And this is the process of mathematical modeling, and understanding this process is central in applications of mathematics. In some sense, we have to remember that modeling is not mathematics. Once we have a model, we can perform mathematical operations on this model, but mathematics will only answer questions about the model and not about the reality. So to what extent the mathematical result pertains to the real world depends on how well the model is connected to the real world. And here actually we enter in the realm of philosophy, and this problem hasn't been resolved as yet, despite really good minds working on this, starting from Plato, through Immanuel Kant, through Bertrand Russell, and many others. Essentially, there are probably, as usual, 3 approaches. One, going back to ancient Greeks, is that God is a geometer. So simply the universe was built using basic understandable structures, geometric, algebraic, and so on. On the other end, at the other end, we have, in some sense, very negative statement. No, whenever we get a correct answer, it is just a pure luck. You are doing just guessing. And then we have something in the middle as usual. The term was coined by Nobel Prize winner Konrad Lorenz, is so-called behind the mirror approach. And he says, well, to a certain extent, such a connection is possible because we have evolved together with the external world, and thus our brain and cognitive powers must faithfully mirror at least part of the world and the rules governing it. Otherwise, we would not have survived. Okay, and we usually will be following this approach. So, if you are a pessimist, mathematics is just the common language of science. If you are an optimist, it is the sixth sense, a link between our mind and the universe. So in other words, the question is whether we can transcend our senses by mind constructs, and these mind constructs somehow correspond to the parts of the universe that are not accessible to senses, to experiment. And then whether we can reliably use these constructs to explain and predict facts that now can be directly tested. So it is up to us, up to you, to choose the approach to follow. Now let us stop considering these questions which have not been solved by really better minds than mine, and just discuss a few examples of successes and failures of mathematical modeling, and whether we really need mathematics in everyday life. So, for example, is there any reason other than mathematical curiosity to ask the following questions? Are there shapes other than a circle that have constant width? So if we measure this across the length, across the particular shape, the figure, the measurement will be always the same. In pure mathematics, we get the answer that of course not, and these are so-called Rouleau polygons. This is the simplest example is this one in yellow. But going back to the question, is it just mathematical curiosity to ask such a question? And the answer is not. If you ignore this question, then you end up in a big disaster. Most of you probably still remember the Challenger disaster. This is actually the picture. The Challenger actually blew up just about 70 seconds after takeoff. What is the relation between this disaster and the previous question? Thanks to very thorough work of Richard Feynman, one of the most famous physicists of 20th century, we know exactly the answer. And just to explain the relation between my question and the Challenger disaster, we have to go back a little bit in time and remind ourselves what happened. So this is the picture of the Challenger shuttle, and what happened was that at the takeoff, the main part at the beginning is played by this white pencils, which are solid fuel boosters. And what happened is that just after the flight, actually there was a fire, the smoke and the fire coming from one of these boosters, and the fire actually very quickly got out of control, and the whole shuttle disaster exploded. Okay, so what happened? To understand this, we just have a look at what happens with these boosters. So this is actually a cross section, and the main character in our story is this rubber O-ring. So this is something which steals joints between pieces of this booster. Why you have these pieces? Well, the idea of the shuttle was that it is a reusable machine. So essentially, parts of the boosters, parts of the liquid fuel engine actually are recovered and then reassembled if possible. So after a liftoff, empty boosters are released from the shuttle, recovered, and then because they are huge, as you can see, the diameter actually of the booster is 11 meters. So it's a huge device. So to make the transport of a booster feasible, actually, when the booster is lifted off from the ocean, it's cut into pieces, then transported back into the factory, and then, of course, these pieces must be put back together. But for this, actually, you have to make sure that each piece is perfectly round. If not, the parts are reshaped, since they have to fit together precisely for the O-rings to be able to prevent fuel leaks. And especially, this is important because, and this actually was the main cause of the disaster, in low temperature, rubber loses its elasticity. So you can imagine that if, for example, these boosters are not perfectly round and the O-rings is round, and if it is not really elastic, then there's no way it can really seal the gap. And Feynman actually found that NASA test for roundedness at the time of the Challenger disaster was to measure the longest distance across the cross-section at just 3 different places. And if the 3 measurements were all the same, then the booster was declared perfectly round. So, for example, this is the picture of a circle according to NASA standards of 1986. So this was one of the major reasons for the Challenger disaster. Probably people didn't pay attention to the fact that you really have to find slightly other way of checking roundedness of an object. So this is an example of a link of really pure mathematics, geometry with real world. So let us go back to a slightly more theoretical frame. As I said earlier, in my mind, we should follow the behind the mirror approach. So, I mean, we should treat our mind constructs with sort of like a reasonable doubt, but we believe, but we have to make sure that everything works. So, but once again, we trust that we can transcend everyday experience in a way consistent with the structure of the universe. And hence the correctness of our models is not a pure coincidence, but it is really a reflection of the laws of nature. However, we should always be aware of the limits of the applicability of the model and how far we can push the model. So let us talk a little bit about principles of mathematical modeling. Oh, sorry. Okay. Sorry. Okay. Oh, sorry. I am just okay. So by mathematical models, we understand abstract structures, often equations that describe some observed phenomenon and that provide quantitative explanations and ideally predictions. And an example of a model is equation describing the motion along straight line, Newton's law, given here. And by mathematical modeling, we mean the process by which we build and analyze such structures and compare observations to the predictions that the model makes. And this is my version. Probably you have seen this picture in various disguises earlier, but this is my sort of like take on the graph of mathematical modeling. So we start with nature, society, or engineering. So there must be real objects we are interested in. And here there is a very nice quotation from Amos notices. We are of this world and nothing comes entirely from within ourselves without reference to the external world. And to understand, sorry, what happens in nature, we try to build a model. As I said earlier, a model usually is an equation, but quite often it's geometric also or algebraic structure. And then this is actually a very important point in which you can take 2 paths. One, let us say, typical engineering path is, okay, once you have a model, once you have an equation, we simply fit this equation into the computer, get some data, and check whether the data are consistent with observations. If they are not consistent, then we go back to the drawing board and we model, we build an improved model, and essentially we move in this circle. I will tell you later, why this approach is a little bit dangerous, but let us focus still on the picture. The other way, which actually usually mathematicians or mathematically minded people take, is that, okay, once you have a model, we first try to understand the model. We try to understand what are the features of solutions, what are the features of the model, how far we can push the model, and so on. So we call this an analysis of the model. And then again, if you are in sort of like applied mode, so if you work for a company, then you, after analysis, actually you go to computations and do this loop again. But quite often, if you are more mathematically minded, you take the model which appeared as sort of like representation of some real object, but then you forget about the object, the original object, and you start working with this model as a mathematical structure. And you can play different games mathematicians do. And quite often, coming from this, we really move into pure mathematics. And in pure mathematics, actually, you can go again. Within the pure mathematics, you can devise your own ideas and then analyze them. But quite often, the point is that the application actually is waiting for you just behind the corner and then jumps at you when you don't expect. The classical example is one of the most famous mathematicians of 20th century, Hardy, who was so appalled by First World War that he decided he vowed not to work on any applications of mathematics, no applied mathematics for him. So he concentrated on number theory, but lo and behold, in 50 years, number theory is at the center of applications of mathematics in the form of cryptography and designs and so on. So quite often you have objects which for a long time resided in completely esoteric world of pure mathematics, and then suddenly started feeding into the nature and society or engineering. So essentially, this is a sort of like interconnected graph of thinking about relations of real objects and abstract structures. So I would like to emphasize once again that mathematical modeling is not mathematics. It is impossible to prove that the model is correct. In fact, we mathematicians say quite often that all models are wrong. There are no good models. The practical question is how wrong they have to be not to be used. So essentially, the value of the model is in its usefulness, not in its correctness. There are, however, very bad models and models that are good enough. For example, a good model should have predictive powers. A model based on available observations should give correct answers in a wider range of cases. And classical examples are coming from physics. Physics actually is a very good field for mathematical modelers. For example, general theory of relativity was really a mind construct of Einstein, slightly prompted by some inaccuracies of Newton's mechanics, essentially around the perihelion of Mercury. But Einstein didn't know anything about light deflection, so the fact that light passing close to heavy objects actually bends, or gravitational waves which were discovered a couple of years ago. So Einstein didn't know about them, but his theory actually predicted them, and we know that they exist. For physicists, Dirac equations, Dirac was also one of the greatest minds of 20th century in physics, and he derived his equations and decided the symmetry requires that there is a positively charged particle of the mass of electron. And actually it happened that it was discovered later. Also, quite recent discovery, Higgs boson, it also was predicted on the basis of theoretical construct. This called standard theory. It is one of the very few examples here which is not a differential equation, it's algebraic structure. And also a good model should contain earlier working models as subcases, and again, classical examples are special or general theory of relativity, contains Newton's mechanics, also quantum mechanics yields the same results as Newton's mechanics for large distances, large energies. So these are examples of relatively good models. Not perfect, as we know, for example, still we don't know how too much general theory of relativity with quantum mechanics. So it's an open question. But there are also very bad models, and bad models coming from really great minds. Just to introduce this bad model, let us go back to Greek times, and just to remind some high school geometry. Platonic solids are solids having the same polygons, spaces, and the same solid angles. We know at this moment 5 Platonic solids. Plato himself knew 4 such solids, and he built a model of the universe by identifying them with 4 elements: water, earth, fire, and air. Okay. When his disciple discovered the dodecahedron, now called Platonic solid, and Plato had 2 options. Most professors would try to somehow hide this discovery, but Plato was actually a great scientist, and he simply accepted the new finding and identified this dodecahedron with what he called God's particle, God's element, or the universe itself. However, it is not actually this model which I was talking about. Here comes Johannes Kepler, who essentially paved way to Newton's mechanics, and he considered this to be his greatest discovery. So there are 5 Platonic solids and 6 known planets in his time. Is it a coincidence? And he decided not. And in 1596, in his work Mysterium Cosmographicum, Kepler observed that, if on a sphere with radius of the orbit of Mercury, we circumscribe an octahedron on which we circumscribe a sphere, then its radius will be equal to the radius of the Venus orbit. If on this sphere we circumscribe icosahedron and a next sphere on it, the sphere's radius would be equal to the radius of Earth orbit, and it goes on. So the dodecahedron would correspond to Mars, tetrahedron to Jupiter, cube to Saturn. He built a model of the universe for the solar system. In the following way. So essentially, you had concentric spheres, sort of like divided or sort of like separated by subsequent Platonic solids. Beautiful model, but completely wrong, as we know. So the beauty and logic of the model and its agreement with observations do not ensure the correctness of them. Now, let me go back to this point which I emphasized earlier. Should we, at this point, when we have a model, we have, for example, we derive a differential equation or an equation of some process. Should we simply go to the computer and do simulations, or should we actually do some analysis of this model first? I had a discussion about this with a British applied mathematician, And essentially, he said, why bother? Just run the equation through a computer and you will always get something useful. And the point is that if you do something like that, quite often you end up with a disaster again. And the example here of the disaster is the Havilland comet. Some of you, I mean, probably not, you don't remember this in person, but might have heard that the Havilland comet was the first commercial jet, passenger jet, constructed in Britain. And after several successful flights, in January 1954, comet broke up in mid-air off the Isle of Elba, killing 35 people on board, and just 3 months later, comet on charter to South African Airways crashed near Naples with a loss of all 21 passengers and crew on board. Okay, so how these two things are linked. So these are pictures of two comets. At the top is the first production, the first model of the comet. The planes which crashed actually were of this design, and here is the later post-catastrophe comet. Just let me enlarge the picture. Just compare the shape of the windows. This is the first production, the first model, and this is later. Quite a difference. Yes, we are going from square windows to round windows. And this is not a coincidence. Namely, well, the remnants of both fuselages were recovered, and you can see here what happened. Essentially, you can observe cracks occurring exactly at the corners, close to the corners of the windows. Okay, so this is actual picture, and this is sort of like a representation of this. Now, for people who are not familiar with mathematics, with theory of elasticity, when you, the fuselage is covered with metal, is an elastic material, and you describe the behavior of an elastic material using systems of differential equations, and there are two main quantitative outputs of when you solve such differential equations. Namely, you calculate the displacement. So this is essentially how pieces of the material move against each other under some force, and the other is stress. So it is what is the internal force between these pieces after when they move. So we have displacement and the stress. Now, if you do calculations, numerical calculations, close to, you have a square gap, square opening here, like a window. You can see here, you calculate the displacements, and that is probably in any calculation. If you see red, then it is bad. Here, displacements are very nice here. There's nothing wrong, nothing really bad is happening at the corner. So if you are looking only at the solution given by displacements, you will not see anything wrong. However, if you move to stresses, to the forces between pieces of material, then you immediately see that corners actually produce very high, very bad stresses. And this is essentially the explanation of what happened to comet. So while the displacements behave well, the stress at the corners increases dramatically. In mathematics, we call it the gradient catastrophe, because the stress is expressed by gradients, by derivatives of the displacement. The occurrence of large stresses does not have to be really dangerous. However, repeated high and very localized stresses will cause metal fatigue and eventually cracking of the metal. Moreover, stresses are very localized. You can see here that actually, if you are a little bit away from the corner, you will not notice the stress. It is something which is called in elasticity theory, the Sandman principle. So why Comet was designed the way it was designed? So as I said earlier, typically the equations are formulated just using displacements. So when you solve the equations, when engineers were solving the equations, designing the fuselage of Comet, they, at the first step, they saw only displacements. And as we earlier saw, displacements are nice. Displacements behave very well. So you don't see any singularity. Only a thorough analysis of the equations, which studies in particular the regularity of solutions, the properties of the derivatives of the solution, can reveal the occurrence of the gradient catastrophe. Also, if, for example, you are not aware of possibility of sort of like localized singularities, you can design your numerical method with too few points. So points at which the solution is numerically evaluated by a computer. It is much cheaper. So you tend actually to use as little these numerical nodes as possible. So if too few points are used, then the scheme may fail to discover large stresses that only occur close to the corners. Thus, potentially the engineers were simply oblivious to the potential occurrence of the gradient catastrophe and thus to the dangerous metal fatigue. So there was no Feynman investigating this catastrophe or both catastrophes. So this is my conjecture. Most likely the accidents were simply due to sloppy numerics, which ignored mathematical analysis of the models. The computational algorithms were designed without understanding the singularities of the solutions and how they impact the accuracy of the calculations. Can I ask how much time do I have?
I would suggest maybe 5 minutes more, but then we should have some questions.
Okay, probably I will maybe quickly go through this. So how to avoid this? First, and this is actually a universal call coming from mathematicians usually, but usually unheeded. Think before you start any calculation. Think. Start with thinking, not start with calculations. Try to understand the properties of solutions based on the structure of the model. This is what mathematical analysis is about. In this case, there is a well-developed mathematical theory which allows for revealing the occurrence of gradient catastrophe. And this theory provides exact descriptions of how bad is the solution close to the corner, and thus how to remove the singularities and carry out standard numerical calculations. And the last topic, I'm not an expert, but everybody now talks about machine learning, artificial intelligence, and so on. So I usually like to put my few cents worth into the discussion. So increasing abundance of data requires new methods of their processing that, due to the limitations of our nervous system, must be computer aided. We cannot avoid this. And this processing mostly consists in statistical fitting of given data to the existing formulae and models. And in this way, in a fully automatic way, in a short time, we can obtain a large range of parameters describing and comparing data sets, expectations, medians, variance, correlations, and so on. Thus, correlation, I will not go into details. Correlations is simply a statistical concept quantifying the observed co-occurrence of events. So this is examples of correlations. And the problem is that people and also, I mean, humans and machine learning and human and machine intelligence quite often use correlations in modeling. And the point is that using correlations in modeling requires extreme care, as it seems that our mind evolved to interpret correlations between events as a signal that there is a causal relation between them. Remember, correlation is not causation. And there is actually a website given here. This is actually a former law student who was so bored that he started collecting spurious correlations. So look at what processes or what events are almost perfectly correlated. On the top, you have the per capita cheese consumption and the number of people who died by becoming tangled in their bed sheets in the state. Perfect correlation. Second graph, which I present here, is divorce rate in Maine against per capita consumption of margarine. Also, very good correlation. So, question is there any causal relation between these two sets of events or not? One can think about possible relations, but I think that this is a good example of spurious correlations which will not carry with it any causal relations. This is also another similar warning set of pictures. All these sets of data have the same mean in both directions, the same standard deviation, the same correlation. You can even draw a figure of I mean, dinosaur. It's called Datasaurus, with the same property. So just if you depend in your analysis only on correlations and other statistical parameters which you get from your machine, then actually you can end up with really very bad models. Okay. And probably it will be a good idea to stop here. So thank you very much.
Thank you very much, Professor Banasiak, for your very interesting talk. Are there any questions? Are there any questions in the chat? And maybe. Well, let me ask you a question then. Early on in your talk, you spoke about the circle and the wrong way of determining that it's a circle. What is the current way, the best way of determining that something is a circle? I'm assuming that they have learned from their mistakes.
To be honest, I don't know what is currently done in NASA, but probably, I mean, okay, probably the sincere answer is that I don't know. I don't know what they are using at this moment.
All right. Any other questions? Well, apparently not. I thoroughly enjoyed your talk. I'm sure I'm speaking for all of us that it was a very accessible talk, and thank you very much. And I look forward to seeing all of you again at the next talk of the Royal Society of South Africa. Thank you very much.
Okay, thank you very much then. Thanks.
Thank you, Jacek.
Thanks.
Thank you, everybody. Thank you, Professor Banasiak. Thank you, Bert. Thank you.